Okay, good morning, everybody. So today's lecture, we're continuing with interfaces. Today we're implementing a stack that's going to implement a stack interface, but the implementation of the stack is a little bit unusual, at least for I think most of you here who haven't done who haven't done anything other than 101, 121 before. So first thing I want to do is I want to make an interface for the stack, for our stacks. So it is in the slides, but I'm going to show it to you on Eclipse instead. So if you have the course, code under the interfaces package, you'll find all of the code that I've been talking about for stacks. Right. So what we want is we want an interface. Right? So this particular interface is an interface for a stack of strings. Right? So the only thing these stacks can hold are strings, which is a little bit unfortunate. But in a week or so, well, maybe a couple of weeks, I'm going to show you how you can make a stack of anything. Right? So I'm going to show you how to make a generic stack. But for now, we have a stack of string. Right? We'd like to have a method called size so that you know how many, so that the user of the stack class knows how many elements are in the stack. We've got this method called isEmpty, right? So this is a little new, right? So we have a method that's a default method in an interface, right? Now notice that the default method, it also has a body, right? So this method actually has an implementation, which you normally don't see in an interface, right? So normally an interface just has a list of methods and that's it. A default method's allowed to have an implementation, and I'll explain exactly why we have these things in a moment. Right? Now, notice that the implementation of the default method, right, I want to know, is the stack empty? So the way you check if the stack is empty, you check the size of the stack. Right? If the size of the stack is 0, then it's empty. Right? So the implementation uses another method that's in the interface. Right? So keep that in mind. That'll be important in a moment. Right? Every stack should be able to push an element onto the stack. Right? Remember, this is a stack of strings, so you're always going to be pushing strings. Right? And every element should be able to pop an element from the top of the stack. Right? And when you pop the element, you get back a string. Right? Oops, sorry. You get back a string. Now, you'd also like other methods in the stack probably as well. Right? So you'd probably want equals. So test if two stacks are equal. So they have all the same strings in the same order. You probably want toString so that you can print a stack. If you implement equals, you have to implement hash code, so you want a hash code method. The methods from object don't go into the interface, because any class that implements the interface is already going to be an object. It's going to inherit from object. So you don't put those in the interface. And you're actually not allowed to put them in the interface. If you try to put in toString, for example, it will complain. So for example, if I try to override the toString method that I get from object, it will complain. It's supposed to complain. That's fascinating. It's supposed to complain. That's interesting. So I'm sure I tried this. Oh, wait, hang on. Yeah, it's not supposed to do that. I'm sure the notebook even says that you're not supposed to do that. Anyway, carry on. Default. So what is that default interface method? So an interface is allowed to have what are called default methods. Right? So classes cannot have default methods. Right? So you're not allowed to have a class that has default method. But an interface can have a default method. So a default method has an implementation. But when you implement the method, you can only use methods from the interface itself. Right? So if you go back to that, if you go back to our stack interface, right? Remember that I said that the implementation of the method body uses another method from the interface. Right, which is fine. You're allowed to do that. Sorry, back to. So you're allowed to do that. You're allowed to use any method from object. So you can use toString or equals or hash code or anything else that comes from object. And you can use anything that comes from what's called a super interface of the interface. So remember that list is an interface, but it also, we say that it extends the collection interface. Right? So list is allowed to use anything from its super interface called collection. right? So when you put in a default method, you're restricted in the number of methods that you can actually use, right? In particular, you're only able to use the methods that the interface itself can access. Now, why did they put these into the language? So they never used to be in the language. They were added in Java 8 to address the following problem. So when you create an interface and it becomes a widely used interface, right? So something like list or comparable or something like that, right? It becomes impractical, if not impossible, to add new methods to your interface, right? Because when you do that, that breaks every class that implemented the old interface, right? Because now they have to add all these new methods that you just created, right? So if you were to do something like change the comparable interface, for example, so you forced people to put in a new method, right? Then everybody who ever wrote compare to now has to add another method. Right? And that's literally millions or hundreds of millions of classes that have to be modified, right? Well, it's going to affect a lot of people, right? Anybody who ever wrote comparable now, who implemented comparable now has to change their code, right? So that's one of the big problems with an interface, especially the widely used ones. You can't modify them. Right? Now, the problem is Java 8 added a huge feature to the language. So there's something called lambda expressions that we don't talk about in this course. Right? But it was a significant addition to the language and that required modifying many of the existing interfaces. Right? So now you have this problem. You want to add some new feature to the language, but you're going to, you have to modify a bunch of interfaces to add this feature. Right? I can't modify the interfaces without breaking everybody else's code. Right? So they said instead, well, let's put in these default interface methods. So we can put in a default implementation for these methods that we want to add. Right? Anybody else who's already using this interface, if they upgrade their Java version, they now get this extra method for free. Right? They can still override it if they want to, but they get this extra method for free and it has an implementation. Right? So the designers of the language decided that it was preferable to add default methods to the language rather than break everybody's code. And so that's why they exist. Okay, we had an array-based stack, right, of string from before. So we had an array list, adding to the, pushing an element onto the stack, you add to the end of the list. Popping an element from the stack, you remove the last element from the list, right? You can easily change that interface, you can easily change that class to implement the interface, right? And again, if you poke around in here and look at array stack, right, all you have to do is add that. And now it implements the stack interface. Because all of the methods that were in this class, size, push, and pop, right, those were already in our implementation to begin with. So modifying the array stack class to implement the interface is trivial. We have a bigger problem, though, with our array-based list. Our array-based stack that we implemented 2 lectures ago. Right? So 2 lectures ago, I showed you how to implement a stack using an array. Right? And it was a stack of int values. Right? Now the problem is our interface is for a stack of strings, right? Not for a stack of ints. So we cannot change our array-based stack class to implement this interface. Right? At least not right now. But in a couple of weeks, we can fix this. So when I tell you about generic classes and interfaces, we can fix this problem so that you can have an array-based stack of anything, or you can have an array list-based stack of anything, or you can have the stack that I'm going to show you today. Okay, so that's just the code I showed you a second ago. All right, so today I want to implement a stack using something called linked nodes. So the reason I want to do this is because of the push operation. So in your array-based stack or your array list-based stack, pop is always in O1, right? Because to pop something from a stack, you just remove the last element, right? So in an array or an array list, that's you just go and look at the element that's sitting at that location in the array and return that value, right? In the array list, you have to decrement the size of the list, but that's all constant amount of work. Push is the problem. So every once in a while, when you push something onto an array-based stack or an array list-based stack, right, you have to resize the size of the array because you've run out of capacity. right? The size of the stack becomes equal to the capacity of the array. Right? So now you have to do this resize operation. That resize operation has to copy n elements in the stack, so it's always in on. Sorry, so it's whenever you have to do resize, that makes the complexity big O of n. Right? So what I want to do today is I want to try to avoid that big O of n, right? Even though it doesn't happen very often. Right? So it turns out you can guarantee that push will have complexity big O1, but you have to change how you store the elements. Right? So I can't use some sort of standard collection now. I can't use an array-based list or an array-based or an array. Right? So instead, I'm going to use something called a node. All right? So a lot of data structures that represent a collection of elements can be implemented using nodes. Right? Now notice the can be. It doesn't mean they always are. It just means you can implement them using nodes. So a linked list is something that I'm going to show you how to do probably in a couple of weeks, towards the end of the course, probably in the last week or two of the course. Right? So we're going to do that in this course. If you take CISC124, the data structures course, you'll learn about trees. Sometimes you'll learn about graphs in CISC124. Right? If you don't learn about them in 235, you might see them in CISC365. And if you're really interested in graphs, you can go to do Math 401, which is actually the mathematical theory of graphs. Right? But there's a lot of, and there's many, many variations of trees, and there's many, many variations of graphs. So these are very widely used data structures in computer science. They're often described using nodes. Right? So what's in a node? So a node stores an element. Right? So I want to make a stack. I want to implement a stack using nodes. So I have to store the elements. So a node can store an element. It can store more than just the element. You can put many things into a node if you want to. So that's if you have a primitive. If you have a node that stores a primitive value, you actually store the element. If you have a node that stores a reference value, then you store the reference. Right? A node has another piece of information that's really important. Right? So it stores references to 0 or more other nodes. Right? And these references are often called links. Okay? So a node's going to have an element, and it's going to have references to other nodes. Okay, now for a stack is what's called a linear collection of elements. Right? So the elements are ordered in a sequence, right? Starting from the top to the bottom of the stack. And each element is only connected to the next element in the stack. Right? So that's why we say it's linear. Right? If you can draw it out, it looks like a line. So for a stack, a node needs to store the element, right? Or a reference to an element. And it needs to store a reference to the next node that's deeper in the stack. Right? So the top node is going to store a reference to the second node, right? The node underneath it, or the element underneath it. The next node will store a reference to the node underneath it, and so on, and so on, and so on. Right? So this is what it's going to look like. So here's our stack of one element. Okay? That thing there, all of that is a node. Right? So you can see it stores an element. In this case, the string A. Right? And that arrow represents the link. Okay? And so this is a stack of size 1. So the top of the stack is the node containing the A. Right? So there, the A is your element. The arrow is your link. Right? When you push an element onto the stack, right? Now I'm using nodes, right? So I have to make a node object to hold the element. Right? So I need to make a new node. So there's my new node. Right? It's going to hold the element, so I'm going to push a B onto the stack. Right? Now when I make my node, I have to connect it, right? Set the link of the new node to point to the current top node. Right? So when I push something onto the stack, that's going to become the new top of the stack. Right? So I need to say, okay, so that's the new top of the stack. What's the next element in the stack? Well, it's that. Right? So I'm going to set the link from the B to now point to the node A. Right? I'm then going to move the top of the stack so that it now refers to B. Right? And then I'm going to add 1 to the stack size because I just pushed something onto the stack. Right? So now I have a stack of size 2. Right? So I do the push operation again. Right? I'm going to push a C onto the top of the stack. right, you end up with a new node, right, whose next link points to the old top of the stack, right? And now the new top of the stack is the element that I just pushed. It points to the node containing the element that I just pushed onto the stack, right? All right, any more questions so far? Okay. Now, how do you pop an element off the top of the stack? Okay, so first of all, I want to, so when I pop C, right, I want to return C back to the caller, right? I also want to get rid of that node that's sitting up there, right? So I want to remember what the value of C is. So I'm going to obtain a reference to the element stored in the current top node, right? So I'm going to obtain a reference to the C. Oops, where's next? Oh, there it is. Okay, so I highlight the C in red to indicate that I've got a reference to it. I now want to set top to refer to the next node deeper in the stack, right? So in other words, I want to move this so that it points to B, right? Now this thing top, right, that's going to be a field in our stack class, right? So it's going to be a field whose type is node, right? It always refers to the node that's at the top of the stack, right? Now that node there no longer has any references pointing to it, right? The only reference that ever points to a node is either top or another node, right? So this node points to the A, right? Top now points to the B. There's nothing pointing to the C anymore, which means the garbage collector can come along and get rid of that node, right? It may not happen immediately, but it will happen eventually, right? So that node now disappears, right? I just removed something from the stack, so I'm going to subtract 1 from the stack size. And then I'm going to return that reference to the C that I had in step 1, right? So remove the element, return it back to the caller, right? And now I have a stack of size 2. All right, so I want to make this node class so that I can actually implement this stack. Right? So here's the UML diagram for our node that holds a string, right? So our node in a stack holds a reference to an element. So here I've got a reference to a string. Right? I'm saying that the relationship here is aggregation, right? So a node is an aggregation of one string, right? That string is is the element that's stored in the node, right? It's not composition here, right? So you don't own the string, right? We're going to implement sharing here, right? So this is shared ownership, right? So the node has a reference to a string. Now a node also has a reference to another node, which is what this line is showing you, right? So every node has a reference to one other node, right? And that reference is going to be called next, right? Now remember, this can't be aggregation or composition, this relationship here, right? Because aggregation or composition is one way only, right? So if a node is an aggregation of something, the something can't be an aggregation of a node as well, Right, so this relationship here has to be one way. So this is association. All right, so let's implement this linked stack class. Right, so our linked stack class is going to implement the stack interface. Right, so it's going to have push, pop, size, and is empty. Our fields, well, I've got the size, right? So the number of elements that are in the stack. And I don't have a collection of nodes. All I have is one node, right? So all I'm going to do is keep a reference to the top node of the stack, right? And that's it. I only got 2 fields inside of this, inside my class. Okay, now I have the class called node. So inside, right? So inside linked stack, I've got the node class. Right, now remember from the previous lecture, we know that a class defined inside of another class is called a nested class. Right? So node is a nested class. Node is a special kind of nested class. It's called a static nested class. Right? So I'll explain to you what that is on the next slide. Right? So what's inside of a node? Well, the UML diagram tells you what's inside of a node. Right? There's a string and there's another node. Right? So inside my node class, I've got a field called elem. Right? So that's the element stored in the node. And then I have the link pointing to the next node, so that's going to be called next. Right? So every node has a string, and every node has a node. Right? I have a constructor here. You don't actually need the constructor. You can get away with it not using a constructor here. It's nice to have one because you can just call the constructor to set elem and next inside of a node. Right? So all the constructor does is set elem to whatever that value is, and it sets next to whatever that value is. Right? So that's all it does. And that's it. That's all your node class is. Right? So all it is really some information. Right? The element stored in the node, and what is the next node in the stack. Okay, so node is a static member class, which is the simplest kind of nested class in Java. Right? So a static nested class a static member class is just an ordinary class. Right? It happens to be defined inside of another class. Right? Now, unlike the other kinds of nested classes, so I told you what an inner class was last lecture, right? So unlike an inner class, a static member class cannot refer to the private members of the enclosing class. So this is a static nested class. So node cannot see size and top. Right? So node knows nothing about the stack class itself. Right? So you should think of node as being completely independent of stack. Right? Stack, however, can see inside of node, but node cannot see outside of itself. Right? So node can't see the details of stack. Right? So in other words, node does not have access to the private fields of the linked stack. Instances of a static member class can exist in isolation from the enclosing class. Right? So all that means is you can have a node object without having a linked stack object. Right? So if you could if this class was public, right, somebody could actually make a node without ever having to make a linked stack object. Right? So in other words, nodes can exist in isolation of stacks. Right? Okay, now the reason that these static nested classes exist is because they occupy a little bit less memory than the other types of inner classes. Right? So the other inner classes are allowed to look outside of themselves. Right? So if this was not static, the node can look into the linked stack object and find its size and top. Right? But under the hood, the only way you can do that is if every node has a reference to its linked stack object. Right? So if this is not static, you've got a hidden field in here that points out to the enclosing object. Right? So that takes up some memory, which you don't want to have to pay for, especially in this case, because you can have a stack with a lot of elements in it, right? Millions of elements, and that's going to eat up a million extra references that you don't need. Right? So you should use a static member class when you can, as opposed to using an inner class. All right, so what does the rest of the linked stack class look like? Well, it's pretty easy to implement. Right? So to make an empty stack, you just set the size to 0. Right? Now, what's the top node in an empty stack? Well, there is no top node in an empty stack. Right? So you just set top to null. Right? And there's your empty stack. Right? What's the size of the stack? Well, that's easy to implement too. It's just the size of the stack. Right? Okay, now, to review very quickly, how do I push an element onto the stack? Right? So here's my stack of size 1. I want to make a new node, right, to hold the element. Right? So how do you make a new node? You call the node constructor. Right? So there's my new node. Right? What do I do next? I make that node point to the old top node. So I set the link to point to the new top node. Right? What do I do next? I move top so that it points to the new node. Right? And finally, what do? I increment the size by 1. Right? Well, that's all easy. Right? Make a new node, so that's a constructor call. Set the link. Right? So set that link to point to the old top node. That's easy too. I can do that in the constructor, or by calling the constructor, sorry. How do I set the top node? Well, that's easy. I just assign this top to point to the new node, and then I increment the size of the stack by 1. Right? So this is trivial to do. Right? Make a new node, so call the constructor. Right? Store the element in the node, and make the node's next reference point to the current top of the stack. Right? So the constructor sets the next link of the node to point to the current top node. Right? So that's steps 1 and 2. Step 3, set top to refer to the new node. Okay, so this top equals n. Right? Step 4, Add 1 to the stack size. All right, this size plus plus, and away you go. You're done. Right? So this is very easy to do. Right? Once you get your head wrapped around what a node is. Now, how do you pop an element off the stack? Well, I need to get a reference to that element there because I want to return it back to the caller. Right? So that's step 1. So I'm going to make a reference to that string. Right? So what does that mean in Java? That means I'm going to make a string variable. I'm going to assign it to the element in the top node. Sorry, I'm going to assign the element of the top node to a string variable. Right? Set top to refer to the next node deeper in the stack. So this is cute. You're going to set top to point to top next. Right? So I'll show you that in a second. Right? Step 3, you're going to, well, step 3, that happens automatically. Step 3, subtract 1 from the stack size, and then return the reference. Right? Okay? So ignore the if statement for now. I'll come back to the second. Step 1, get a reference to the element in the top node. Right? Well, the element in the top node is just this top.elem. Right? So I can store that in a variable type string. Right? Step 2, make top point to the next node. Right? So this is the cute part in this implementation. Right? You're going to set top to equal this top next. Right? Because top.next is the pointing to the next node in the stack. Right? And then you're going to decrease the size by 1. And then you're going to return the old top element. Right? The garbage collector will take care of disposing of the old top node. It won't dispose of the string that was stored in the top node because you've got a reference to it right here, right? And then you're returning that back to the caller. So the caller is going to have a reference to it too, right? So the string inside the node doesn't disappear. All right, now what's this if statement doing, right? So you can't pop an empty stack, right? So you have to do something if someone tries to pop an empty stack, right? So if someone pops an empty stack, you can't, for example, return the empty string, right? So this method has to return something, right? Or throw an exception, right? There's no way you can return back a string that means that an error has occurred, right? Because there's no way you can guarantee that that string's not in the stack, right? So rather than trying to return some error value here, you should throw an exception, right? So if the stack is empty, throw an exception, right? Yeah, you should throw an exception. This one throws a runtime exception. There actually is a special stack exception that's defined inside the language because the Java has its own stack class in java.util. All right, so there's pop. Okay, anybody have any questions about push or pop? This step here is the one that you have to wrap your head around, right? When you assign this top to equal this top next. Right? That might look a little weird to you. It might look a little strange to you, right? That you can assign this top next, right? But you have to remember how assignment works, right? So assignment works starting from the right-hand side, right? So whatever this value is gets stored in this value here, right? So this line is in fact perfectly legal. All right. So that's it. That's your stack, right? That's all the methods that are required of us from the stack interface. Now, if you're implementing a stack, it would be nice if you provided a toString method, right? So that people who are using your stack class can print out the stack to see what it looks like. So what's the problem with toString when you have, oops, sorry. Right? Where is, here, okay. So when I have a stack of size 3, right? So what's the problem with toString, right? So for toString, for a stack, you probably want to print out all of the nodes, right? You want to print, well, you want to print out all the elements that are stored in the nodes, right? But that means you have to iterate over this sequence, right? And this isn't an array or an array list, right? So there's no get, right? I can't get node 0, I can't get node 1, I can't get node 2, right? I now have to iterate over this chain of elements, right? So iterating over a sequence of linked nodes, it turns out this is very common, right? So whenever you're working with a linked structure like a linked list or a stack implemented in this way, right? Or later on a tree or a graph, right? You have to iterate over some sequence of nodes. Right? Okay, now to write this loop, because it's going to be a loop, right? Observe that the end of the sequence is indicated when you hit a null next link, right? So in other words, right, when you hit a link that's null, you know there's nothing left in the sequence, right? So that's going to be our stopping condition, right? So what's the starting condition? Well, you just start at the top node of the sequence, right? So starting at the first node of the sequence, you simply follow each next link, right? Just follow the links to the next node until you eventually reach the null node, right? Now, it turns out you don't have to start at the first one if you don't want to, right? If for some reason you had a reference to the middle node, you could start at the middle node and iterate over the remaining nodes, right? So this works no matter where you start inside the sequence. Okay, but I'm going to assume you're starting at the first element, right? So there's a general pattern for this, right? So here's the general iteration pattern, right? You're going to make a node variable, call it whatever you want, right? I'm going to call it n. And you set it equal to whatever the starting node happens to be, right? So wherever you want to start your iteration from, you make it point to that node. Right? For our stack, this is going to be this dot top, right? Now, all you do is you write a little while loop, right? So while n is not null, right, you can do something with n inside the loop, right? So for example, inside here, I can say n, I can print out n.elem, right? Because n's not null. So I can safely use it to access a field or a method of the node class. Right? So I know that n is safe to use inside of the loop. Right? At the end of the loop, you just update n. Right? You say, well, n's now the next node in the sequence. Right? So n equals n dot next. Right? Now, when you use this pattern, right, down here, what do you know about n? Well, you know n's null because the loop stopped, right? The loop stops when n is equal to null, right? So whatever you do, don't use n after this loop, right? Because if you try to use n here, n's null. So whenever you use n, so if you say n dot next, you're going to get a null pointer exception, right? Your program will crash, right? So whatever you do, if you're using this pattern, don't use n here. All right, but that's the general pattern. So you can just take that pattern and now plug it into toString, right? So for toString, oh wait, this is what it looks like when you do this, right? So I'm going to start n to point to this dot top, right, which is the C, right? Do something inside the loop and then say n equals n dot next, right? So n's pointing here. So what's n dot next? Well, n dot next is the next node. Right? So all you're doing is you're going to follow that link. Right? So whenever you say n dot next, you're following that link. Right? So n equals n dot next moves it to the next node in the sequence. Right? Until you hit null. Right? And when you hit null, that's when the loop ends. Right? Remember, you still have a reference called this dot top, pointing to the top of the stack. Right? So these nodes don't disappear. Okay, so how do I implement toString? I'm going to use string builder to implement toString. So I'm going to use string builder to accumulate the returned string. Right? I'm just going to write here, right? That code right there, that's just the pattern code I showed you back here. Right? N equals the starting node. Well, n is not null. N equals n next at the bottom. Right? So n equals the starting node. While n is not null, do something with n, and then make n equal n dot next. Right? What do I do with n? Well, I append to this string the new line character. Right? Then I append the element. The element's just a string, so that's fine. Right? So what this is going to do is going to print out stack. It'll give you the string stack, and then on the next line it'll give you the first element, and then on the next line it'll give you the second element, on the next line it'll give you the third element, and so on. Right? When you're done the loop, right? Don't use n, but you're done anyway, so I just return b to string. And where is link stack? Right, so there's the code there, right? Does it actually work? Well, it's got a little main method here. So let's run the main method. So the main method pushes an A, B, and a C, and then it prints the size and the stack, right? And then does a bunch of other stuff. Right? So does this work? Don't mind the exception. The exception's intentional. Right? So size 3, there's your stack, CBA. Right? Pop the C, you get to size 2. Right? So you end up with a stack BA. Pop it again. Right? So pop the B, you have a stack of size 1, and it's the A. Right? Pop the A, you get a stack of size 0. The stack is empty. Right? Then you get an exception because I'm intentionally forcing the exception by popping the empty stack. Right? So this toString works just fine. All right. Now that's the normal way of implementing toString. So that's the way most people would write the toString method, right? They would just write a little while loop, follow all the links to get to the next node. There's another way to do this. And this turns out to be not so important for stacks or linked lists, right? But it turns out to be very important when you talk about trees and graphs, so more complicated types of data structures. That node I showed you is an example of what's called structural recursion, right? Every node has a reference to a node, right? That node has a reference to a node. That node has a reference to a node, and so on, right? Until you have a node whose next node is null. Right? But every node has a node, right? So that's recursive, right? So the recursive structure makes it very easy to write recursive algorithms, right? So it's natural to write recursive algorithms when you have these node-based structures, right? So consider toString, for example, right? So toString I implemented with a loop using iteration, right? But I can implement it using recursion. Right? So there's my public toString method. Right? It starts out the exact same way. So I start out with a string builder. Right? I then make a variable called node. I then make a variable n, whose type is node. Right? And I set it to the top of the stack. I then call a recursive helper method called toString helper. Right? And I pass in the top node. Right? That method is going to return the string representation of all of the nodes. Right? So I'm going to write stack, right, colon. Then on the next line, I'm going to write the first element, then the third element, then the fourth element, and so on. Right? On the next line, write the first element, then on the next line, write the second element, then on the next line, write the third element. That's all going to be done by the recursive helper method. Right? So here's my recursive helper method. Notice that it's private, right? So it's not public, it's private. It's private because to call the method, you need to pass in a node, right? And anybody outside of the class, they don't know what the node class is because the node class is also private. Right? So you don't want anybody calling this method. You only want to be calling this method from within the class itself. Right? So toString helper is just going to print out a new line. Or sorry, it's not going to print out. It's going to give you the string that starts with the new line character, followed by the element stored in the node, right? Followed by all of the other elements after this one, right? So one more time. What does the recursive helper method do? Right? So it's going to print out. Well, it's going to generate the string for this node. Right? So it generates the string for this node. And that's just new line followed by the element. Right? And then it's going to generate the string for all the other nodes. Right? So the string for all the other nodes. So how do you generate the string for all the other nodes? Well, you just call itself, passing in the next node. Right? So when it calls itself, you get a new version of toString helper, right? That node n is now the next node in the sequence, right? So what's that going to do? Well, it's going to print out that, it's going to generate the string for that node, right? And then it's going to generate the string for the next node in the sequence, right? So what does that do? Well, that runs another version of toString helper, right? Which generates the string for that node. Right? And then generates the string for all the other nodes. Eventually, and next will be null, right? So that's when the recursion stops. So the recursion will stop when that node is null, and then in that case, it just returns the empty string, right? And so that also works to generate the string, right? So there's two ways of doing this, right? You can use the iteration method, right, which I think most programmers find to be the easiest to write, right? Or you can use the recursive method, right? Now, to do the recursive method, you have to practice your recursion, right? When you become good enough at recursion, it usually becomes, so for things like trees or linked lists or these other linked structures, it's usually much easier to write the recursive method than it is to write the iterative version of the method, right? For linear structures, it's usually easier to write the iteration version as opposed to the recursive version, right? But for the other types of data structures like you'll see in 235, it's usually much easier to write the recursive version of the methods, right? But that's how you can write the recursive version of toString if you wanted to. All right. Anybody have any questions about node-based data structures? This is going to pop up again. So it's going to show up again when we talk about linked lists, because a linked list is just a list implemented using nodes. All right? And it's going to show up in 235 over and over and over and over again. OK? I think that's it. Yeah, that's it. Super. See you on Wednesday.